All right, welcome. Today, we're going to talk about something you can't see, but it's everywhere. It powers pretty much everything in our modern lives. I'm talking about electromagnetism. Yeah, that phone in your hand, the lights over your head, it all comes down to this amazing, powerful link between two forces. So, let's dive in and uncover the secret, shall we?
So let's kick things off with a question. Think about a simple battery. You know, the kind that powers a flashlight. Now, think about a magnet, maybe one that's stuck to your fridge. What in the world do those two things have to do with each other? I mean, they seem totally unrelated, right? Well, it turns out there's a secret connection, a link that was discovered over 200 years ago, and believe me, it completely changed everything.
So here's our game plan. We're going to start with how electricity has this secret power. Then we'll figure out how to map its invisible field. After that, we'll see how you turn a current into actual motion, and then we'll flip that idea on its head. We'll also see how we generate our world's power and finish up by looking at the two different kinds of magnets that make all this happen.
All right, let's get into it. And you know, the story here doesn't start with some big planned out experiment. Nope, it all started with a complete accident.
So, let's set the scene. The year is 1820. A guy named Hans Eristed is giving a lecture. He's got a basic setup on his desk. Just a wire, a battery, and kind of off to the side, not even part of the main event, is a regular magnetic compass. He wasn't planning on using it at all, but what he saw next, it was one of those aha moments that changes science forever.
Okay, so here's what the setup looks like before he does anything. The switch is off, so there's no electricity flowing through that wire. And the compass, well, it's just doing its thing, pointing north like a good compass should. Totally normal, nothing weird going on, yet.
But then, this is the moment. Ørsted flips the switch. The current starts flowing, and bam! The compass needle just moves. It jerks away from pointing north and swings around. He couldn't believe it. There was only one possible explanation. The electric current flowing through the wire was creating its own magnetic field. That was it. The hidden link between electricity and magnetism was finally discovered.
So that's a huge deal, right? An electric current makes a magnetic field. But that leads to the next big question. What does this invisible field even look like? Is there a pattern to it? How can we figure out which way it's going? We needed some rules of the road.
Well, the way we visualize this invisible force is with something called magnetic field lines. And you can actually see this effect. If you took a wire, ran a current through it, and sprinkled tiny iron filings around it, you'd see something amazing. The filings would automatically arrange themselves into perfect circles around the wire. Those circles, that's our map. That's what the magnetic field looks like.
Okay, so we know the shape is circles, but which way are those circles going? Clockwise? Counterclockwise? How do you know? Well, the cool part is you don't need some complex scientific instrument to figure it out. In fact, you have the tool you need right with you, right now.
Yep, it's your own hand. This is called the right-hand thumb rule, and it is so clever and simple. Go ahead, you can do it with me. Imagine a wire with the current flowing upwards. Take your right hand, super important it's the right one, and point your thumb up in the same direction as the current. Now, just naturally curl your fingers. See that? The direction your fingers are curling, that's the exact direction of the magnetic field. So simple, but so powerful.
All right, so let's recap. We know a current makes a magnetic field, and we even have a handy trick to know which way it's going. That's cool. But the next question was, so what? What can we do with this? And the answer to that question would lead to one of the biggest inventions ever, creating movement on purpose.
This is where things get really interesting. What happens if you take our wire with its little circular magnetic field and you put it inside a different, much stronger magnetic field, say between the north and south poles of a big magnet? Well, those two magnetic fields are going to interact. They're going to push and pull on each other, and the result is a real physical force. The wire actually moves.
And you probably guessed it, there's another hand rule for this. But listen carefully. This time you have to switch to your left hand. This one is called Fleming's left-hand rule. So, take your left hand and make like a little finger gun. Point your first finger straight out, your middle finger to the side, and your thumb straight up, all at 90 degrees to each other. It's easy to remember. Your F first finger is for the F field, your center finger is for the C current, and your thumb points in the direction of the M motion. Field, current, motion. Got it?
Okay, now let's use that rule to build a simple DC motor. You start with a loop of wire sitting in a magnetic field. You run a current through it. Now, using Fleming's left-hand rule, you'll find that one side of the loop gets pushed up and the other side gets pushed down. And what does that do? It makes the loop start to spin. But wait, there's a problem. After it spins halfway, the forces would flip and push it back the other way. It would just twitch back and forth. So how do you get it to keep spinning? That's where a really clever little gadget called a split ring commutator comes in. Right at the halfway point, this little ring flips the direction of the current in the loop. By flipping the current, it keeps the push going in the same direction of spin. It's this constant, perfectly timed flip-flop that creates continuous rotation. And just like that, you've turned electricity into motion.
Okay, so we've seen that electricity can create motion. That's huge. It led one of the greatest scientists of all time, Michael Faraday, to ask a really brilliant question. He thought, well, if electricity can make motion, could it work the other way around? Can motion create electricity?
And the answer Faraday found was a massive, world-changing yes. He called this phenomenon electromagnetic induction. But, and this is super important, there's a trick to it. You can't just let a wire sit still inside a magnetic field. Nothing will happen. The magic word here is change. You have to be moving the wire or moving the magnet. Something has to be changing. It's the changing magnetic field that actually creates or induces an electric current.
And you knew this was coming. There's a hand rule for this too. But pay attention, because this is where people get tripped up. For generators, we go back to the right hand. It's still Fleming's rule, just the right-hand version. The setup is identical, finger gun, but what each finger represents is a little different because our goal has changed. This time, your thumb is for the motion, the direction you're pushing the wire, your first finger is still for the field, and now your center finger tells you which way the current will flow. So we use motion to find the current.
Now, this whole idea of electromagnetic induction, this isn't just some neat trick for a science lab. This is it. This is the fundamental principle behind how we make almost every single watt of electricity that powers our entire world.
And what's so cool about this is the perfect symmetry of it all. Think about it. A motor uses electricity to create motion, a generator uses motion to create electricity. It's the exact same principle, just running in reverse. They really are just two sides of the same incredible coin.
This chart really lays it all out perfectly. You can see how they're mirror images of each other. The principle for a motor is force, for a generator, it's induction. The energy conversion is flipped. Electrical to mechanical for a motor, mechanical to electrical for a generator. And look at the key parts. A generator has simple slip rings, but a DC motor needs that clever split ring commutator to keep it spinning in one direction. And, of course, the big takeaway, use your left hand for motors and your right hand for generators. Simple as that.
Okay, we're almost done, but there's one last important thing we need to cover: the magnets themselves. It turns out the magnets we use in all these amazing devices come in two basic types.
So on one hand, you have permanent magnets. Think of the ones on your fridge. They're made of steel, and they're just always magnetic. They're always on. But on the other hand, you have electromagnets, which are basically just a coil of wire wrapped around an iron core. And why do we use these so much? One word: control. With an electromagnet, you can make it stronger or weaker just by changing the current. You can flip the north and south poles just by reversing the current. And most importantly, you can turn it completely off. That ability to switch it on and off is why they're used in everything from giant cranes at scrapyards to the simple doorbell at your house.
So let's boil this all down. What do you absolutely need to remember? Number one, an electric current always creates a magnetic field around it. Number two, the reverse is also true. A changing magnetic field creates an electric current. Those two ideas are the building blocks for everything. They lead to motors, which give us motion, and generators, which give us electricity. And don't forget your handy hand rules to figure it all out. And I want to leave you with this final thought. This perfect symmetry we've been talking about, electricity makes magnetism and magnetism makes electricity, it's just such an elegant principle of how our universe works. A motor really is just a generator running backwards. So it gets you thinking, right? Where else in science can we find these kinds of powerful opposite and equal ideas that are the keys to understanding, well, everything? Thanks for digging into this with me.